Hello, this is Dr. Hanaa Assil, and this is about halogenoalkanes. So this is mainly for Unit 2 of AS Chemistry at Excel, but you can use it as a reference for reactions and characteristics of halogenoalkanes. So let's take a look at a brief review of what we said. Remember, we need to classify halogenoalkanes. This is in the same way that we classified alcohols. So we look at the carbon to which the halogen is attached. If that carbon is bonded to one carbon, then it's a primary halogenoalkane. If the Br or the halogen is bonded to a carbon that's bonded to two carbons, then it is secondary. If the carbon is bonded to three other carbons, that is a tertiary halogenoalkane. So if the question says which is a tertiary halogenoalkane, well, let's take a look. CHBr3 is this, and each Br is attached to a carbon actually that doesn't have any other carbon, so these are primary. Now, when we have this compound, the Br again is bonded to a carbon that is bonded to only one carbon. That again is a primary. This one, the Br is bonded to a carbon that's bonded to three other carbons. That's a tertiary halogen. While that last one is again a Br that is bonded to a carbon that's bonded to only one carbon, so that's a primary. So we're asked which one is tertiary. It is that one in which the Br is bonded to a carbon bonded to three other carbons. Compound X is a halogenoalkane. Name this compound. Do you remember how to name a compound? We said we look at the longest chain. So here we have four carbons bonded one after the other. And then we need to see what are the substituents. So I have a chlorine at carbon number 2. And I have a methyl group at carbon number 3. Can you see that? So how do we name this? First of all, we count from the side that gives a lower number for the substituent. Which substituent should I mention first? The chloro or the methyl group? Well, we use alphabetical order. So I have to say 2-chloro-3-methyl, not methyl and then chloro. We arrange them, if we have several substituents, we arrange them alphabetically. So 2-chloro-3-methyl butane. Which compound is hydrolyzed most rapidly? You should remember that if we have a carbon bonded to halogens, which one will break more easily? Which one is weaker? Now, if we have a carbon bonded to a halogen, as I go down the group for halogens, group 7, the halogen gets larger, so there is less attraction between the bonding pair of electrons and the positive nucleus. So as I go down, the bond becomes weaker, more easily broken. So if I'm comparing between carbon and different halogens, the one that has the bigger halogen will break off easily. But here in our choices in this question, all of them are chloro. So what is the difference between them? You should remember that if we're comparing the same halogen, then a tertiary will break more easily than a secondary will break more easily than a primary. So 1-chloropropane, that's a primary. 1-chlorobutane, again a primary. 2-chloro-2-methyl-propane, that's a tertiary. 2-chlorobutane, that's a secondary. So the one that will hydrolyze most rapidly, the one that will break the C-Cl bond faster is the tertiary halogenoalkane. Again, we have these two compounds, one with a chlorine and one with an iodine. Compounds X and Y both react with cold dilute potassium hydroxide. Cold dilute potassium hydroxide replaces the halogen with an OH. Now explain how the rate of reaction of Y will compare with that of X. So which one will react faster? That means which of these bonds will break faster and react with the hydroxide? We said the one that has the Ci bond is faster because a Ci bond is weaker, more easily broken than a CCl bond. Halogenoalkanes undergo nucleophilic substitution, just like alcohols. So if we react it with a nucleophile, again, we said a nucleophile is a species with extra lone pair of electrons. So this could be cyanide, ammonia, hydroxide. These lone pair of electrons are used to attack the slightly positive carbon on the halogenoalkane. The electrons in the bond between the C and the Br go to the Br, so that my other product is Br minus, and I replace the halogen with the nucleophile that is attacking. So please remember, when we have a halogenoalkane and we're reacting it with hydroxide, we have two types of reactions that could happen with a hydroxide. Either aqueous hydroxide or hydroxide in presence of water. In that case, the Br is replaced by OH, and that is a nucleophilic substitution in which the OH is acting as a nucleophile, attacking the slightly positive carbon and removing the Br. But if we react the halogenoalkane with hydroxide in presence of alcohol or hydroxide in presence of ethanol, in that case, we do not replace Br with OH. What happens is an elimination reaction in which the hydroxide is acting as a base. Please note, in this case, the hydroxide is acting as a base. It is removing that hydrogen on the neighboring carbon. The electrons are used to form a double bond. The Br is removed, and we end up with an alkene. So please remember, halogenoalkanes with hydroxide. In presence of water, you're forming alcohol. In presence of ethanol, we're forming an alkene. So 1-bromobutane reacts with alkali. The mechanism and type of reaction here is what? What is happening? The hydroxide is replacing the Br. So that is hydroxide in presence of water, so it is replacing the Br, and we said that is a nucleophilic substitution reaction in which the hydroxide attacks the slightly positive carbon and replaces the Br. 1-bromo-2-methyl-propane can be converted back to 2-methyl-propane-1-ol. So I have the halogenoalkane. I can react it with aqueous alkali. Identify and correct 3 mistakes in this mechanism drawn by a student. What is wrong with this? Remember, we said, first of all, the dipoles on the carbon and the Br are reversed. The student wrote the carbon is slightly negative and the Br is slightly positive. It's the opposite. Bromine is more electronegative than carbon, so it is the bromine that is slightly negative and the carbon is slightly positive. Then the student has an arrow going from the slightly positive carbon to the OH. That's wrong. It should go the other way around. We said lone pair of electrons on the hydroxide should first of all be written, and the arrow goes from the lone pair of electrons on the hydroxide to the slightly positive carbon. 1-bromo-2-methyl-propane can be converted to 2-methyl-propene. So in this case, I am forming the alkene. So what should I add? Changing halogenoalkane to alkene, I react it with potassium hydroxide in presence of ethanol. Heat under reflux. The hydroxide acts as a base, takes the hydrogen on the neighboring carbon, and forms a propene. Compound X is a halogenoalkane. The reaction of X with hot concentrated ethanolic KOH produces two isomers. Again, hot concentrated ethanolic. So KOH in presence of ethanol. We said KOH in presence of ethanol, that is elimination, in which we are forming a double bond. So either the double bond will remove the H on that methyl group on the left, or the hydrogen on the neighboring carbon. So these are the two possible isomers of alkenes that could be formed. Iodine monochloride is a covalent compound produced by the reaction of iodine with chlorine. Iodine monochloride is a dark brown liquid. The equipment shown can be used to pass chlorine gas over solid iodine to produce iodine monochloride, ICl. When excess chlorine is passed through the U-tube, the iodine monochloride reacts to form iodine trichloride. First of all, write a chemical equation for the reaction of iodine and chlorine to produce iodine monochloride, and we're asked to include state symbols. Please be careful. If the question requires state symbols, please make sure you put them. So what are we reacting? We're reacting chlorine with iodine. Of course, each of these are diatomic, so iodine plus chlorine, and we are told it will give ICl. First of all, we need to balance, and we are required to give state symbols. We are told already that the iodine is a solid, the chlorine is a gas, and up there in the question it says that the iodine monochloride is a dark brown liquid. The question says iodine monochloride molecule has a permanent dipole. Complete the following table using electronegativity data from your data booklet, and hence show the dipole on the diagram of the iodine monochloride molecule. So at the end of your exam there is a data booklet. One of the things in there is a table of electronegativities. So you get these numbers from the data booklet, and what we have is the chlorine has electronegativity of 3, iodine has electronegativity of 2.5. That means the chlorine is the one that is more electronegative, so that is the one that will be slightly negative, and the iodine is slightly positive. Iodine monochloride reacts with propene to form two isomeric products. This is an addition reaction that is similar to the reaction of propene with hydrogen halides. Draw the skeletal formula of both isomers. So we're starting with propene. We're reacting with ICl, and that means we're going to open up the double bond, put an I and put a Cl. Well, where are we going to put the I and where are we going to put the Cl? That is the two isomers. So either the chlorine is in the middle or it is the iodine that is in the middle. Now the question says explain which of these isomers is a major product. You should remember that in order to form these products, the double bond attacks the slightly positive end of the electrophile in this case, which is the ICl, and we put the I first. That means the other carbon becomes a carbocation. And if you remember, you should remember that a secondary carbocation is more stable than a primary carbon. So if I put the iodine on the carbon in the middle, then the carbon on the end would be a primary. That's less stable. So that is why we put the I on the end, and then the carbocation in the middle is now a secondary carbocation that will be attacked by the lone pair of electrons on the Cl minus. So this is the major product, 2-chloro-1-iodopropane, because the iodine has partially positive charge. It is attacked by the pi electrons of the double bond. to form a secondary carbocation. So when we put the I on the end, the carbocation is in the middle. That's a secondary that is more stable than if we put the I in the middle, then the carbocation is on the end, and that would be a primary carbocation, which is less stable. Alcohols can be produced from the reaction of halogenoalkanes with aqueous alkali. Draw the mechanism for this reaction with 1-bromopropane. Show the lone pair involved in the mechanism and any relevant dipoles and curly arrows. Again, we said if we have halogenoalkane and we react it with aqueous alkali, then we replace the Br with OH and form the alcohol. Now, how does this happen? Again, we said this is nucleophilic substitution. The lone pair of electrons on the O attacks the slightly positive carbon, and the electrons of the bond between the carbon and the Br go to the Br, so that my other product is Br minus. The reaction of 1-bromopropane with concentrated alcoholic alkali forms a different organic product. Name the type of reaction and give the displayed formula of the product. Again, if I'm starting with 1-bromopropane in alcohol, so this is KOH in ethanol and heat. The name of the reaction in this case is elimination, because what I end up with is the alkene. Compound 2-chloro-2-methylpentane has 6 carbon atoms. It can be converted into a tertiary alcohol with aqueous sodium hydroxide. Again, aqueous sodium hydroxide means the hydroxide replaces the Cl. Now, what class of reagent is the hydroxide in this reaction? Of course, the hydroxide here is acting as a nucleophile. It uses its lone pair of electrons to attack the carbon and replace 2-chloro-2-methylpentane undergoes an elimination reaction that produces an alkene. Complete the reaction mechanism with the appropriate curly arrows. State the essential condition for this reaction. So in this case, we're trying to make an alkene. That means the OH minus is acting as a base. It's taking the proton, giving the electrons to form a double bond, and replacing the Cl. So the next thing that happens is that the electrons of the CCl bond go to the Cl to form an alkene. The other product is water, Cl minus, and of course this happens when we have hydroxide in presence of alcoholic solvent or in presence of ethanol. Complete the general equation for hydrolysis of the bromoalkane. State symbols are not required. So if we are hydrolyzing this, that means we are removing the Br, putting an OH, and my other product is HBr. 1-bromobutane reacts with alcoholic ammonia when heated under pressure. State the type and mechanism of this reaction. Okay, remember, if I have halogenoalkane like 1-bromobutane, for example, and I'm reacting it with alcoholic ammonia, what happens is the ammonia replaces the Br. So this is a nucleophilic substitution. Remember, the type is substitution. The mechanism, how it actually works, is nucleophilic substitution. Name the product formed. If I'm starting with 1-bromobutane, my product would be 1-aminobutane. Propene can be formed by heating 1-bromopropane with alcoholic potassium hydroxide. Again, when we say alcoholic potassium hydroxide, which reaction is happening? Elimination to form an alkene. Remember, if we were using aqueous, it's just a substitution of the Br with OH. Alcoholic, or in presence of ethanol, it is an elimination to form an alkene. Bromocyclopentane reacts when heated with aqueous sodium hydroxide according to the following equation. So again, with aqueous sodium hydroxide, what they did is replace the Br with an OH. Complete the mechanism for this reaction. Again, the OH. Remember, this is what is written, so we need to include the lone pair of electrons on the OH, an arrow, a curly arrow, from the lone pair of electrons on the OH minus to the slightly positive carbon. The electrons between the carbon and the Br go to the slightly negative Br, forming that product. And of course, my other product is Br minus with its lone pair of electrons. Classify both the type of reaction and mechanism shown. This is a substitution, nucleophilic substitution reaction of replacing the Br with an OH. What type of bond fission is this? If we're breaking, remember, what type of bond fissions do we have? It is either heterolytic, in which both electrons go to one of the atoms, and this is what is happening here, to form ions, so this is heterolytic. We also had another kind of bond fission which we named homolytic. This was in the free radical substitution reactions of alkanes, in which the electrons that are being shared go one to each atom. In this case, we form free radicals. That was called homolytic. But what is happening here is both electrons go to the halogen, so this is a heterolytic bond fission. 4 isomers with the formula C4H9Br are shown. Which of the isomers are primary halogenoalkanes? Tell me. Which of these are primary? Can you see which ones are primary? Q is a primary with the Br on the end of the chain, and R is a primary with the Br at the end. In the preparation of 1 bromobutane from butane 1-ol, it is preferable to react the sodium bromide with 50% sulfuric acid rather than concentrated sulfuric acid. Remember, when we were reacting the alcohol with a Br, the reagent here was KBr in 50% sulfuric acid, not concentrated sulfuric acid, and we're told the main reason for this is what? Remember, when we were talking about halides with concentrated sulfuric acid, we said KBr, for example, concentrated sulfuric acid will form HBr. But the HBr will react again with the sulfuric acid because it's a strong reducing agent, and this forms bromine instead of the HBr. So we don't use concentrated sulfuric acid because that would cause the HBr to be oxidized to bromine, and we need the bromide ion to be the one that reacts with the alcohol. Bromoethane reacts with dilute aqueous potassium hydroxide in nucleophilic substitution to form ethanol. Again, complete the mechanism. If we complete the mechanism, we said the lone pair of electrons on the oxygen will attack the slightly positive carbon, and the electrons in the bond between the CBr will go to the Br, which is slightly negative. Now the question says, explain the meaning of nucleophilic substitution. What does nucleophilic substitution mean? Remember, the word nucleophilic means the oxygen in the OH minus donates a lone pair of electrons to form a dative covalent bond with the carbon. The word substitution means the OH minus ion displaces the bromine, so the OH replaces the Br. Another question, which of the following are properties of the liquid 1-bromobutane? Now, 1-bromobutane is a halogenoalkane. Do you expect it to be soluble in water? Do you expect it to be affected by a charged rod? Okay, remember which kind of liquids are affected by a charged rod. We said if something is polar and we put it in a burette, we open the tap, we bring a charged rod next to it. If the liquid is polar, it is diverted, or the stream bends towards the charged rod or away from the charged rod. That indicates that the molecule is polar. So first of all, is our molecule polar? Yes, it is polar, so it will be affected by a charged rod. But remember that this is an organic compound. Organic compounds do not dissolve in water. Chloroethane can be produced in various ways as shown below. Identify by name or formula the reagent needed for each of these reactions. So I'm starting with C2H6. That's an alkane. How do we make a chloroalkane from an alkane? We react it with chlorine. Of course, if we're asked for the conditions, then we need UV light. What about if I want to make it from an alcohol? We said alcohol. I want to replace the OH with Cl. I react it with PCl5. What about from an alkene? I want to change an alkene to the chloroalkane. I add HCl. Chloroethane will react with alcoholic ammonia initially to produce ethyl amine. So if I have CH3Cl, CH2Cl, chloroethane, I react it with ammonia. We said the ammonia will replace the Cl, and my other product in this case is HCl. What type and mechanism is that? Again, that is nucleophilic substitution. Now, why can they act as a nucleophile? We said the ammonia, the nitrogen on the ammonia has a lone pair of electrons that can attack the slightly positive carbon on the chloroethane. A reaction mechanism is shown. So, which mechanism is this? We are removing the Br and we're replacing it with an OH. This is, in this case, the hydroxide ion is acting as a what? The hydroxide ion here has lone pair of electrons attacking a slightly positive carbon. It's acting as a nucleophile. Consider the reaction mechanism shown. In this case, the bromide ion is acting as what? Remember, this is an alkene with bromine. So we said the first step, alkene goes to the slightly positive Br, and the electrons of the bond go to the Br minus. This forms a carbocation. So the Br minus, the bromide ion, is attacking, using its lone pair of electrons, it's attacking a slightly positive carbon. Again, the Br minus here is acting as a nucleophile. The compound with formula this can be made by reacting alcoholic ammonia with what? How can I put an NH2 on a carbon? I react it with a halogenoalkane. The halogenoalkane, the ammonia will react with the halogenoalkane and replace the chlorine so that I get that compound on top. Products of the reaction when 2-chlorobutane is heated with sodium hydroxide depend on conditions. Again, halogenoalkane with hydroxide depends on conditions. What condition is needed to produce alkenes? What condition would be needed to change the chlorobutane to but1-ene or but2-ene? That means I'm trying to form alkene. That means I need sodium hydroxide with ethanol or alcoholic solvent. In that case, the hydroxide is doing an elimination reaction. What condition would produce the alcohol? So if I'm starting with 2-chlorobutane, I add sodium hydroxide in presence of what? In order to get the alcohol, in order to replace the Cl with an OH, I need it as an aqueous solution. Do we understand all of this now? So, I hope this was useful. This clarified some things about halogenoalkanes, and thank you for listening.